First of all, I would like to thank the organizers for the kind invitation. It's a great opportunity to speak here. In this talk, I will introduce our ongoing joint work with my student Cai-Yun Ma on one-sided multifractal analysis. So first, let me give a brief introduction to the classical multifractal analysis of measures. Okay, let mu be a probability measure on the real line. So in multifractal analysis, people care about the local dimension of mu. So the local dimension of mu at a point x is defined by d mu x equal to the limit r tends to 0 logarithm of mu at x minus r, x plus r, over r. Okay, if the limit exists, otherwise, if the limit does not exist, we can consider the up local dimension. We use d bar mu x to denote, and lower local dimension d mu x, okay, to define the up and lower limit. So the multifractal analysis aims to describe the dimension of a level set of local dimensions. There is a well-known fact that if mu is a good measure in some sense, for instance, if mu is a self-similar measure or self-affine measure or self-conformal measure, satisfy the so-called open set condition. In that case, mu will satisfy the so-called multifractal formalism. Okay. Oh. Okay. In a sense that for all alpha greater or equal to 0, the Hausdorff dimension of the level set of the local dimension of mu, okay, that's the point such that the local dimension of mu at that point is equal to a given point value. That's called the level set. Okay. So the Hausdorff dimension of this level set is equal to, also you can change the local dimension to up local dimension, also equal to the lower local dimension equal to alpha. And all these guys is equal to the Lambda transform of the LQ spectrum of mu, which I will define later. Okay. Okay, all of them are equal to the supremum, infimum alpha q minus tau q, where q take all values on R. Here, tau q denotes the LQ spectrum of mu. Which is defined by tau q equal to the limit, lower limit r tends to 0, logarithm summation of a supremum of a summation of a mu xi minus r, xi plus r to the q's power over log r. Here, the supremum is taking over all disjoint connection xi minus r, xi plus r collects over intervals with center xi in the support of the measure. Okay, so that's if we have such an equality, the Hausdorff dimension of a level set of local dimensions of a measure mu equal to the Lambda transform of the LQ spectrum. In that case, we call mu satisfy the multifractal formalism. If the level set is empty, we can take a convention that the Hausdorff dimension of an empty set equal to negative infinity. Okay. In that case, actually we can take alpha to be any number. Don't care about whether or not the level set is empty or not. When mu is self-similar measure or self-conformal measure satisfies separation condition, this probability holds. And in a general case, it's still a challenge question. If there is no separation condition, then we don't know whether or not the formalism always hold or partially holds on a given alpha. Okay. Okay, so I will not talk about too much about this. Now we would like to consider one-sided multifractal analysis. Okay. Okay. Yeah. Again, we let mu to be a probability measure with a compact support on the real line. Okay. In this case, we define the one-sided local dimension of a mu. So the one-sided Okay, it's defined by, so we write dr mu x to be the limit r tends to 0 log mu x plus r divided by r. Okay, in this case, we only consider one half part when we define the local dimension from x to x plus r. So that means when we consider point, choose x, but we only consider this part. Okay, in this case, one may ask the same question. How about the dimension distribution of level set of one-sided local dimensions? Okay, so that's the limit. If the limit does not exist, we may simply consider the one-sided lower local dimension and up local dimension. Okay. Okay. So this is a natural question. One would like to know whether or not one-sided local dimension will share the same property as local dimensions. Okay. There is one general result says actually for all probability measures on the real line, for almost all point x, the local dimension and the one-sided local dimension, they coincide for almost all mu. So this is known. But whether or not they're equal in the sense of the dimension of level sets, the result says no. In general, the one-sided multifractal analysis may be different from the two-sided one. Actually, it's Kenneth Fairclough who initiated the study of a one-sided multifractal analysis. So let me just write here. In 2004, Kenneth Fairclough considered the one-sided multifractal analysis for Alf's regular measure. So let mu be S-dimensional Alpha's regular measure on the real line with S between 1 and 0. Okay, that means for any point on the support of a mu x minus r, x plus r, always bounded by constant times r to the s power. So for any x in the support of a mu, and any r, for instance, less than a fixed value r0 and 0. Okay. If this property holds, we call mu is Alf's regular measure. Here, s is assumed to be a value strictly less than 1. So the support of a mu is a complex set. Okay. So in this case, we know that the local dimension of a mu at any point in the support is equal to s. So there is only one local dimension, essentially. But how about a one-sided one? Okay. So for the one-sided one, can us get two results. Oh, yeah. So he proved that first, for the lower local dimension of a mu, except for countable many points in the support of a mu, the lower local dimension is still the same as the local dimension, no problem. But there are many points such that the upper local dimension actually is greater than S. Actually, for any alpha greater or equal to S, the Hausdorff dimension of up local dimension of X equal to alpha is given by S squared over alpha. Okay. So this result says, indeed, for the up, one-sided up local dimensions, this guy has quite different behavior than the up local, two-sided local dimension, because in that case, still equal to S. Okay. So that's a result of Falconet. However, Falconet only considered this the so-called S alpha regular measures. So there is a natural question: how about more general fractal measures? Is this a typical situation? So that's our motivation. So we wouldn't like to investigate the one-sided multifractal analysis for more general measures. For instance, self-similar measures or self-conformal measures. Okay. So now let me give some setting of our investigation. Okay. I'm not sure, maybe that's better. Maybe this one, good. Oh. So actually, we are going to consider the classical Gibbs measures supported on self-conformal sets satisfies strong separation condition. Okay, let fi I from 1 to m be a C1 IFS on real line. That means each function fi is a contractive mapping on the real line, which each function is C1 is C1. And we let K to be the attractor. So by Hutchinson theory, we know that K is the unique compact set such that K is equal to the union of the images of a K under the mapping Fi. So there is a unique non-empty compact set K. So K actually is called a self-conformal set because on the real line, any C1 function is a conformal if the derivative not equal to 0. Yes, yes, it's a contractive one. Okay, so this is attractor K, and we can assume that this IFS satisfies the strong separation condition. So this is an assumption. Strong separation condition, that means Fi K intersect Fjk equal to empty set for any I not equal to j. Okay. Also, we may assume that each function fi is a monotone increasing. So fi derivative always greater than 0. So let me draw a picture here. Suppose there's an interval. Fi will map this interval into itself. Okay, so there's one F1. And maybe here I will call the Fm. And somewhere. Okay, these intervals may intersect each other, but we did guarantee that they have no intersection restrict on K. Okay. Okay, so this is our setting for our self-conformal set. Now we needed to consider the Gibbs measure restrict on this self-conformal set. So we let capital sigma denote the symbolic space on the alphabet 1 up to m to the nth power. This is a one-sided full shift space. And we can let small sigma to denote the left shift map. Okay. And we can define a Gibbs measure on the symbolic space. Okay, here Gibbs means there exists a continuous function on the symbolic space such that restrict on the cylinders. So the measure is controlled by the potential of a G. So it's an exponential Sngx, where Sng is a back-and-forth sum G plus G composite sigma plus up to G over sigma to n minus 1. Okay. So that's a Gibbs measure on the symbolic space. Now, we would like to consider its push forward and the coding map associated with the IFS. Okay. Sorry. So just, oh, sorry. So we know that pi to denote the coding map from the symbolic space to the self-conformal set K is the coding map. Defined by pi x equal to the limit of f x1 composite f xn at 0, where n tends to infinity. Okay, for any given point x on the symbolic space. Okay. So any point on the symbolic space using this composition, you will get a unique point. Okay. So this is the so-called coding map, and we can let mu equal to the push forward of eta, right? Yes. So this measure, of course, is supported on K. Okay. So now our purpose is to conduct one-sided multifractal analysis of mu. Okay. So this our target. So just this measure mu. Okay. So right now we can let E R mu x so to be the level set such that the one-sided local dimension, or one-sided local dimension of mu equal to alpha. Okay, for any alpha great or equal to, sorry, this should be alpha. Yes. Similarly, we can define over 9 ER alpha and lower E alpha. Okay, here we replace the local dimension by up or lower local dimension. Okay, one-sided local dimension. And we would like to investigate the Hausdorff dimensions of this three level sets for given alpha. Okay, now we can state our result. To state before that, maybe it's better to first give one lemma. Okay, Okay, so just okay. Let's first define some potential phi from the symbolic space by R by phi x equal to logarithm of absolute, no, not necessarily absolute value, because our potential the derivative is assumed to be positive. So this is just the fx1 derivative at pi sigma x, okay, for x in the symbolic space. Okay, so that's phi x. And then we can first give a general lemma to analyze one-sided local dimension. So what's is the one-sided local dimension in this case? Okay. Okay, the first lemma says for any point in the symbolic space, the up local dimension of mu at pi x is given by the up limit of n tends to infinity here. That's back of sum as n gx plus g at the special point lower m, I will explain what's this, times n sigma nx. Also, I will define this, what is this function, capital N, as n phi x. Okay. Also, you can consider lower one-sided local dimension. So also this one. If you change up local dimension to lower local dimension, you simply need to change the lower limit. Okay, from the upper limit to lower limit. So here, the function g is the potential for our Gibbs machine mu, eta. And here, there is phi. Phi is the potential here. Okay. Now, what is m? M is the special point that, so we can also denote as m to the infinity. It's just the point all the coordinates are m. Okay, so just there's a special point on the symbolic space, and there is another function n. So for any point in the symbolic space y in the symbolic space, ny is equal to the supremum of a k such that m to the kth power is the prefix of a y. So that means what this letters appears in the first k letter in y. So that means y1 equal to yk equal to m. Okay, so that's the ny. So the proof of this result is quite direct. Okay, so for instance, when you consider the one-sided point here, suppose you consider this is pi x somewhere, and you consider one-sided pi x plus r. So you will first look at in the nth step pi x in some cylinder in the symbolic space. So, and then you need to care about how much is this point. What's the distance between this point to the right end point of that cylinder? Okay, if this point is very close to the cylinder, then this number n could be very large. So in this case, the measure on this small part is much smaller than the measure of a mu on this cylinder. Okay. So that's the expression here. Now, to help you to understand this difference between the one-sided local dimension and the two-sided one, so I just want to write what's the expression for two-sided one. So if you consider two-sided one, it's simply the limit S n gx over S n phi x. Okay. And also here you can change the limit to a lower limit or up limit. Okay, so that's a so you will see the difference. So you will see the only difference is that here there is one special potential, not potential, function, capital N. Okay. Okay. So that's the local dimension. Now, if we use ER alpha to denote the level set of one-sided local dimensions, we can state our result. Okay, here we write our result. So let alpha be a real number greater or equal to 0. The first result is E of alpha not equal to empty set if and only if that the lower ER alpha not equal to empty set if and only if that alpha between A and B, well, A is equal to the minimum of the ratio G d nu and phi d nu. Well, nu is a more invariant measure, sigma invariant measure on the symbolic space. Okay, and similarly B equal to the maximum. Okay, also this nu takes over all sigma invariant measure on the symbolic space, and the dimension were equal to the supremum of h nu negative integration of phi d nu. Well, there's a ratio g d mu phi d mu equal to alpha. Okay. So that's the first part. Actually, this result is the same as two-sided one. So there is no difference when you consider the one-sided local dimension or the no one-sided local dimension. In that case, the level set has the same dimension as two-sided one. So no difference at all. The interesting case is for the level set for up lower one-sided local dimension. So I will write here. So the part, I will write part 2. Okay. E are alpha not empty if and only if that alpha greater or equal to A. Well, A is defined above the minimum ratio of G d nu over phi d nu. Okay. Where nu takes over all invariant measure on the symbolic space. And the dimension E, the upper one is equal to, we give a variational principle for all alpha greater or equal to A. The Hausdorff dimension of level set of this up one-sided local dimension is equal to the supremum. Okay, so this a little bit long, the formula h nu divided by negative. So negative. So yeah, it's negative. Integration of a phi plus phi m gm and times the potential alpha phi minus g d nu, and with a constraint that integration of g d nu, sorry, maybe two, no, this one, phi d nu less than or equal to alpha. Okay, that's our expression. So H nu denote the measure theoretical entropy of nu. Nu is here. Nu is taken over all sigma invariant measure on the symbolic space. Satisfy this condition. Alpha, the ratio is less than or equal to alpha. Okay. For the two-sided one, the dimension also has a similar formula, but here is an equality. If there is an equality, then there's a term disappear. Okay, but now we just have an inequality here. Okay, so that's the expression. So I still have some time, so I just want to give some idea how can we get this maybe upper bound. Just say why this is an upper bound. Yeah.
Sorry, can I ask you one question? So
yeah.
in level 1, you have this correction with G of M.
Yes.
So what is M? Is this an arbitrary vector?
M is so you have one special point on the symbolic space called xn, but we ask xn or equal to m. So just denote this special point on the symbolic space. The coding is just given by the lattice m. Okay, so I use m, lower m denote that special point.
But you take any n. No,
m is the last map, the left endpoint. So if you consider the right endpoint of a k, the symbolic coding is that point. Okay. Yeah. Thank you very much for your question. So now let me give a rough explanation why we have such an expression. Oh, sorry. Oh, sorry. Okay, so in number 1, we give the expression of one-sided local dimension. So you will see that in the expression there is a special function n y there. So according to this expression, we see that x is a point in E up ER alpha if and only if that there exists arbitrarily large n such that okay, Sn gx plus gm n sigma nx over Sn phi roughly equal to alpha equal to 0, 1. So of course this we can put alpha on the other side. So you will see that if and only if that Sn g minus alpha phi x plus gm n sigma nx equal to little o n. So that's very easy to see. So this also gives you the information that n sigma n x is almost equal to Sn alpha phi minus g x over g m plus little n, yeah, something like that. So that's quite easy to see. So you can see that this point x, we can give a natural cover of this point. So this point x is contained in so contained in this x1 up to xn, then m to the n sigma x. So the symbolic x is contained in this cylinder x1 to xn, then m to the n sigma x. And if you consider that this cylinder use the coding map projecting to k, you can calculate the diameter. Okay, the diameter is equal to, almost equal to expression of Sn. So this guy has a diameter close to be Sn phi x, and this one has a diameter plus, so phi n, and n sigma nx is this ratio. So S n alpha phi minus g x over gm. Okay. So now we can cover this set E alpha by all such possible cylinders, and the diameter of this cylinders has this form. But I was cheating. Actually, you cannot take all such a cylinder because you still need to guarantee one issue. The one issue is that this guy should be greater or equal to 0. But how can we guarantee that guy is greater or equal to 0? Is this part greater or equal to 0? So we have some restriction about the cylinders. So the cylinder here should satisfy additional assumption is that Sn, so we have a constraint so constraint is here is Sn alpha phi minus g x less than or equal to 0. Okay. Oh no. Yes, alpha phi less than or equal to 0. Okay. Yeah. So now you can use some dynamical formalism to consider the S power of all the sum, and consider some partition function, and you will check that if you would like to get a value S such that the summation of all this term is finite, then the critical point turns out to be the value satisfied this form. Okay, this is just use some dynamical formalism. So this is for the upper bound For the lower bound, we need to use the method of a concatenation, and also the Moran constructions use a similar method that I used with De-Jun Feng and Junwu in our any paper. Okay, so that's some rough idea of this case. So one might ask us the natural question. So here, the measures are very good. It's Gibbs measures on self-conformal measures satisfy strong separation condition. What about the higher dimensional case? For higher dimensional case, for instance, if you consider a measure on the plane, when you consider some local dimension, you can choose, for instance, you can only consider one part, or even consider some local dimension along some cone, right? You can define that. And in that case, what would be the one-sided multifractal result? In this case, yeah, for instance, in the right-hand side, in this part case, we can only handle some very special self-conformal measures or self-similar measures on the plane. For instance, this rotation-free of self-similar measures on the plane or in the higher dimensional case. Okay, even this case, the result could be more complicated than this one. Okay, it involves in this case, it involves some projection of self-similar measures on the x-axis. In that case, you have some overlaps, and also the structure of the measure around the right endpoint is quite special. So, but in any case, we can handle this case. But in this more general case, the situation looks quite mysterious. Go back to the self-similar measures on the real line. If you don't put the strong separation condition, but instead of an open set condition, the result seems there is no uniform result, as I see. In some case, the one-sided and two-sided one are the same, but in some cases there's some different result. But it seems that no very general result like this, no uniform result like this. Okay, I stop here. Thank you. Yeah.
I'm just trying to compare your result with Faulkner's result. So for the lower version, in your result, do you differ by just a countable set or anything uncountable?
You mean this one?
So in this one, it's only countable.
Yeah, still countable.
And in your set, it's still
countable. No, but there's not a constant in the general case, right?
okay, sorry.
Yeah, in general, it's still, since this is not alpha regular, you have many different value. Okay.
Does it differ from the...
Yes, so you can check that even for the first part, it's different, but the formula you will see is the one-sided one and the two-sided one has no difference when we consider the local dimension and the lower local one-sided dimension. But the difference appear on the upper one. So for the method, Kenneth used the theory of ubiquity. And here we want to use, actually we use thermodynamical formalism and also the technique of Moran construction. Okay. Yeah.
How about the Faulkner's result on plane?
Yeah, the good question. A good question. Actually, that depends, really depends how you define the one-sided one, right? Yeah. In a plane, you can take some dimension along cones or half planes. So this really depends how you choose. Okay.
There's no results for none.
Yes, there's no result. So it's quite it's quite interesting to know what will happen in the plane.
Yeah, so you define the right-sided.
Yes.
You could do the left-sided, replacing n by 0.
Yeah, that's exactly would be the same. Yeah.
Yeah, and so could you like find points for which the right-sided behavior is not the same as the left-sided behavior and describe the two?
Yes, that's possible. That's possible. So in that case, if we remove the assumption that we will have one assumption that I is greater than 0. But if you remove this one, then you need to consider both sides. And in that case, the potential part, this part, you need to add one more time. Okay. Yeah. I think still you will get a similar result. Yeah. Yeah.
So can you do similarly for the analysis x plus r over 2, x plus r? So the one-sided, but between x plus r over 2 and x plus r.
Let me think. The good question I think we can handle, I guess. If the only thing is that we need to find out expression that we give in lemma 1 in that case. I think so. Yeah. I think it's still related to that function, capital N. Yeah.
Here, the formula is the same. The Falconer's both take the middle term, the simplest unforced regular measure I know.
Yes, if you ask that's a regular, you will go back to Falconer's result. Yes, you can recover that. Yeah. Yeah, looks complicated, but in the concrete case, this can be precisely calculated. Just use, consider some extreme value, use calculus, you will get a precise result. In that case, in Falconer's case, O phi and G only depends on one letter, and also this new runs over just this ballooning measures, so it's quite easy to get a result. You can recover Falconer's result.
Let's then do something again.
Okay, thank you.